right, well, good afternoon, everyone. Thank you for coming. Almost. All right, we'll blame it on the dongle. So yeah, today Neerav and I are going to be talking about some of the work that we've been doing around XDP, the Express Data Path, where we've been working on one of the use cases for XDP in load balancing and how we're trying to accelerate that using hardware offloads. So kind of an overview for those of you who don't know what XDP is, then we'll talk about it briefly. If you're here to learn about XDP and what it is, not the session for you, but the slides will be posted, I think. We do have a lot of data in here. Then we're going to talk about some NIC hardware capabilities, kind of how network interface cards work, and then where does XDP fit in that whole pipeline, and then what our goals are. What are we actually trying to solve with this work that we've been working on? Then Neerav is going to talk about what are these hardware hints that we're talking about, how are they helping, how do we pass metadata between the actual hardware and up to these programs, how do we program the hardware to send us the data that we want, and then what everyone is probably waiting for is what do the numbers look like? Is this worth it? And then what are our next steps? And then hopefully we'll have some time for questions. So if you're not familiar with XDP, this stands for the Express Data Path. This is an implementation of the eBPF, or Enhanced or Extended Berkeley Packet Filter infrastructure in the Linux kernel. This is a very busy slide, but basically what it's showing you is down at the hardware level, we have a network interface card that's processing packets, and then up into the kernel, in the operating system, we have the physical function software driver. So we have our driver, first software step, right, in receiving a packet. And XDP is giving us this infrastructure to make decisions as to what do we do with packets as they arrive in the NIC. Instead of having them traverse all the way up the network stack to things like NetFilter or TC, we can make these things, these decisions, whether to drop a packet, redirect a packet, modify a packet, very, very early in the packet lifecycle. And some of the real world cases with XDP has shown like immense performance boosts. But that's all I'll say about this. So in the typical hardware pipeline, this is just to kind of familiarize everyone kind of the steps that actually happen, because this becomes relevant as to what we're actually trying to tell the hardware to do. So below the line is really inside the hardware. So we have a packet parser, we have a packet actually coming off the wire, and the first thing that we do is identify it. Is it IPv4? Is it IPv6? So we look at the ether type. So we're looking at the headers, and then from there we start to do things like extracting fields. And this is based on how the NIC is told to parse the actual packet. So if you see like a NV GRE packet or a VXLAN packet, what do we actually want to look at? So from there, then we do some table lookups in the hardware to decide, do we drop it there? Do we have to compute some hashes? Do we want to compute some extra CRCs? Do we have to modify the packet? And so then we go into a compute model in the state machine inside the NIC, and all of this generates metadata, right? What queue did it come in on? You know, what is the RSS hash, or what is some other hash? What are the CRCs, et cetera, et cetera. So with this work that we've been working on, is XDP is a feature in the Linux kernel. It's very agnostic today to the NICs. We would like to keep it that way. So we're looking at it as we also have all these network interface cards in the field that have various levels of hardware offload that they can provide. So how can we leverage what we have in the field to try and speed up these programs? So if we can go ahead and accelerate packet parsing, which is one of the components of XDP programs, is to actually look at the packet, see what it is, make a decision on it, if we can have the program say, here's the data that you're going to parse anyways, we should be able to save some CPU cycles. Yeah, and I mentioned that we want to avoid kernel changes because kernel changes are tough to make, especially around core functionality like this. It also means that we have to maintain it longer term, so we want to have some flexibility if possible. We do want to keep it hardware agnostic, so we are here from Intel. We are looking at this from how do we make Intel hardware faster, but we also want to provide a solution to the Linux kernel that will help the entire industry. And yeah, the best effort acceleration. So where can we accelerate? If one generation of hardware is able to give you 5 different types of hints, the next generation might have 10 different hints. But what we want to do is in the changes that we're going to make or propose, that your programs don't care. They just work, right? If the hardware can provide it, great. If it can't, we'll still do best effort. And the big target is we really have to hit some of these packet processing targets around like 100 gig, 200 gig, 400 gig. As these things are coming, are we going to be helping or hurting that performance? Yeah, and I think Neerav will continue.
So essentially today we have 2 problems to solve with XDP. One is how do we pass this metadata between the drivers or the hardware to the program, the eBPF program running on XDP, and how can the XDP program know what that metadata is or what kind of metadata they really want is what they're getting. So today XDP in Linux kernel already has a way to exchange metadata, which is between an XDP program in eBPF and a socket program. So we are trying to leverage the same infrastructure that is already there so that the same infrastructure can be used for sending metadata between the NIC and an eBPF program. So we are not trying to change that model as it is, has been there today. We're just trying to look to reuse that whole infrastructure. But what we need to modify is, because today the way the eBPF programs are written on this XDP is they don't know what those metadata is. They need to learn what is coming in that buffers. So we need a mechanism for XDP programs or the eBPF programs to program that information. So one of the directions we are looking at is to use, so the way the BPF programs are created are using LLVM and their ELF binaries. They have information about what are the ELF sections and the map sections and different sections of the BPF program themselves. We're trying to see if we can extend that to allow a BPF program to leverage the metadata that is there in the hardware. The way we are thinking about it, instead of making it very hardware-oriented, we want to make it more like a protocol-oriented, like a packet format. So what kind of hints they want is, let's say, anything on the IPv4 headers or TCP headers or offset. Make it a little bit more flexible to go into a generic offset values. So whenever an eBPF program comes up, they can provide this information to as a binary load time, and a NIC driver or a handler can program that into the hardware, so the hardware can generate that metadata for the BPF programs and they can consume it. Now, for experiment purposes, so before we make all this work consumable, we wanted to see whether this is actually making any sense. So PJ, unfortunately, I couldn't travel to Korea. We did this presentation or precursor to this in NetDev conference in South Korea, actually. So we did some experiments with very simple XDP programs where they were just doing packet parsing and dropping packets. And we added hints, which was a simplistic hint of what kind of packet type it is. You know, it's a TCP packet, UDP packet, whatever, and drop the packet. That's it. And so the XDP program did not have to parse the packet to identify the packet. We saw a lot of jump in performance, as you can see on the first graph. I know there are too many graphs in this. So if you see in the green and the blue, so in fact, the simplistic drop packet performance test gave us kind of 100% packet processing boost. Now, that was not the end of it, because that's a very simple program. That's not realistic. So we wanted to test with an actual program like a load balancer, or people use it like a layer 4 load balancer in Edge. So we took that up, and so the load balancers, so we started creating different kind of metadata. So there were two types of metadata we started created. One was just give them protocol offsets and type and not give any information about the header. And as we see, if you see in the graphs, that program, in fact, did not help at all. So that program, in fact, reduced the performance versus increasing the performance. So say, OK, now this is not helping. Let's up the game and see if we can create metadata by adding more IP header information or layer 3 information. Essentially, the BPF programs, what they're doing is they're processing packets, layer 2, layer 3 processing headers. I mean, whatever the pipeline Nick is doing, they're duplicating that. So we wanted to see if we give them that information up front in the metadata itself, they don't have to touch the packet again, and they can make decisions based on that. So we had two variants of layer 4 load balancer running, one with state tracking and one without state tracking. So basically, there was no localization in one scenario, and there was localization. So what we observed when we had this hints that with no localization, no state tracking, it helped tremendously so that they can look at that metadata, make a decision, and get out. But the flip side, when you have a load balancer who is doing all kind of connection tracking and state tracking and having millions of rules in software, the amount of lookup they do does not, so the metadata in that scenario did not help at all. It's like the current packet performance rate was equivalent to not having hints at all. So what we see here is the hints that we have so far are not helping all the different kind of programs. So as next step, what we are trying to do is, OK, we need to analyze further what other hints or maybe lookups that we need to offload so that the XDP programs can focus on their business logic and leave the packet processing to the NICs, all the general purpose NICs that can do that. What are the other programs? May not be load balancer, but there are other stateless programs that can benefit from such kind of metadata and hints. And we have to test, as you have heard in other presentations. Now, we are not trying to test with Spectre and Meltdown kernels. We have to try to test that and see the differences of performance with and without those changes. We want to take this further so we are already working with some of our partners, and we'll take it upstream on Linux kernel because it's going upstream. We will be working with the IOVisor community and the eBPF community in general because we are doing this change into the ELF binaries for the BPF binaries. This is our first time in the OCP, so one of the questions was, okay, how does OCP come together where the Linux is providing data path acceleration, and how we can work together so that the use cases can be like, we can create some kind of a better use case scenario. So that's what we are working on. This is work in progress. Any questions?
So if you have questions, just raise your hand, or you can come up to this mic here.
How is it comparing to DPDK? Did you test it?
Yeah. So DPDK is its own application. This is in kernel, so there are certain applications who do not want to modify. So there are applications based on sockets, standard sockets, and this is bump in a wire kind of an application. So the packet can be modified or changed, or it can be sent back to the standard TCP/IP stack. So your applications running on standard Linux operating systems can use it as it is. For applications, certain applications they are modified and running on DPDK, they can use DPDK. This is for in-kernel acceleration.
It was more related to performance. I'm familiar with XDP and
yeah.
DPDK. Yeah. I'm asking about the performance. Do you have comparison between?
That's our next goal as well, yes. Because it's not ending here. We have to work with AFXDP because that's another thing that's happening in the community, that each socket can have a each socket in the application can have a BPF program running in the socket. So we need to have a pipeline that is running, and now you can have a DPDK-based user space NIC running on an AFXDP or whatever. It needs to work together. So that's a convergence that we have to work on.
Yeah, and for the XDP framework, so Neerav mentioned AFXDP. For those of you who kind of follow the network mailing lists, that used to be called AF Packet. That has morphed into AFXDP. It's very, very new, very, very recent, so the performance around that is still TBD. But it is something that we are signed up to go and investigate.
Others? So I can give you some feedback. First of all, welcome to OCP, and glad you're here. So the networking group within OCP is typically made up of or responsible for devices that the data path is handled in switching ASICs. And so we don't typically hit the CPU to do the forwarding of the data path traffic. Control path, certainly, but not the data path. And so I think you probably get more traction in the server group. So the server group, obviously, they have the NICs, and all the data path there is done in, in software.
Yeah.
So,
Thank you.
Yep.